All right. Hi, everybody there in Econ 140 land. Today, I'm going to walk through part of Lab 3. So here we have our Lab Assignment 3. The goal of this is to explore multiple regression analysis. We've been talking about Chapter 6, multiple regressions, and so we're going to go through and use the home price data set and this electric data set here, both from the Coop website, and run a couple of different iterations of regressions and then interpret the results. And so we'll be using a couple of different model formations. We want to remember that the home price data set is looking at the sale price of houses in Windsor, Canada, and we're going to look at the explanatory variables of lot size, number of bedrooms, number of bathrooms, and number of stories. And we'll run a regression with all 4 of those and then 3 of them and look at the differences in our coefficients, our estimated coefficients, and in the differences in our R-squareds. And then the sort of larger question there is what happens when we leave some of these variables out? What do we get? What's our result? And then we'll do the same thing with the electric data and look at the cost of production of electricity in millions of dollars per year, and then we're going to use explanatory variables of output in thousands of kilowatt hours per year, price of labor in dollars per worker per year, price of capital in dollars per unit per year, and then the price of fuel in dollars per millions of BTUs. And all this information is built into the book, and so if you ever get confused about the units or our variables that we're using from these data sets from the book, they are all, that's a typo, they are all explained in the book. It's not the most straightforward way to find them, but they are all there in these practice problems when they talk about interpreting this data. So let's get started. We're going to start out in Stata. So you want to open up your Stata, and I'm going to go ahead and create a log of my work so I can see what all I've done. I'm going to call it Lab 3 and my name, and I'm going to not put it in data sets, I'm going to put it in there. And that will open that log that will track everything I do today. I also want to open a do file to track my commands. I'm going to make a note up here. It's Lab 3 multiple regression analysis. And remember, you can use those asterisks to write notes, and then your commands are going to come in black text, and so your text will be color coded in your do file. And you want to remember to save your do file. I'm going to actually save it right now. There we go. All right, looking good. So now the first thing I want to do is import the data set I want to use. And I'm getting the little spinning ball of death, which is always terrifying, but hopefully it will clear up for me in just a second. So I'm going to go ahead and import data from Excel. I want to start with the first problem, so I'm going to start with that home price data set. I want to remember to import the first row as variables, and that looks nice and good and clean, and then go ahead and click OK. I also want to copy my log command into my do file and my import command. And remember, you can do that just by, if you go to your review window, my windows are a little bit moved around in doing Excel in the classroom. I moved some stuff around because the screen was so small. So, but you'll have your review interface somewhere that's going to show you every command or error you've had, and you can just click on those commands and they'll show up in your command window down here, and that's an easy way to just copy and paste into the data set. So I'm going to put in here part 1, and that part 1 is called what? Exercise 6.2. So I'll put that, I'll type that in there to let me know where I am. And then the first thing I'm going to do, the first thing I like to always do is summarize my data just so I know what I'm working with. And if I want to look at the summary of all my data, I can just put summarize in. If I want to just look at the variables I'm interested in, I can just go and say summarize sale price, lot size, bedroom, bath, and stories. And there I'll get my variables of interest. So far, so good. So far, hopefully a review. The next thing I want to do is start with my regression. The first regression command I want to use, I'm going to just, as I'm going through this, copy and paste these commands into my do file, is I want to do that first regression, part A, which says to run a regression of lot size on, sale price on lot size, bedroom, bathroom, and stories. And that's the great thing about working with Stata, is that getting the multiple regression, it's the exact same command that we would use for a simple regression. We just add in more independent variables, right? More explanatory variables. So here we get our regression results, and now I want to look at these and interpret them. And so that's what the command, the next part says. It's run a regression of y on x1, x2, x3, and x4. Interpret the 4 coefficients and the r-squared. Discuss the statistical significance of your explanatory variables briefly. And I don't want you guys to kill yourselves on these, but do spend some time, both for your benefit and mine, reviewing the statistical significance test. So looking at things like the p-value, the t-stat, the confidence intervals, and just sort of keep that fresh in your mind, because that's something you're going to want to do every time you run any regression. You're going to want to make sure the first thing you do when you look at your model is make sure your explanatory variables are significant, statistically significant. If they're borderline, how borderline? Is it something we can work with, or something that we might need to throw out or explore further? So I'm going to go ahead and now in my do file and in my log here, I'll put in the asterisks so that I am telling Stata this isn't a command, this is just some prose. I'm going to say the r squared of 0.5355 tells us that this model explains more than 55 or 53% of the variation in sale price. I can tell by the size of the F statistic that the, let's see, how do we want to say that? We can use, so remember we want to use the F statistic to reject that null hypothesis that r squared is equal to 0. So I can tell by the size of the F statistic that it is plausible to reject the null hypothesis that r squared is 0. Yay, first part done. I've now discussed the statistical significance of the r squared and interpreted it and identified it. Good stuff. Now on to the coefficients. The point estimate for lot size is 5.429, which implies that each additional square foot of lot size will tend to increase house sale price by $5.40, let's say 3 cents, rounded up to a reasonable number. This is the important part, right? Now that we're using multiple regressions, we get to hold all other variables constant. So the point estimate for lot size, our beta hat for lot size, is 5.429174. which implies that each additional square foot of lot size will tend to increase house sale price by $5.43, holding number of bedrooms, number of bathrooms, and stories constant. Pretty cool, right? I next want to interpret the coefficient for the explanatory variable. Bedrooms is 2824.61, which implies that each additional bedroom will tend to increase the sale price of a home by $2,824.61, holding lot size, number of bathrooms, and stories constant. Getting the hang of it? Heck yeah, this is getting tedious. Let's do a super simple version of it. So we could say a marginal increase in the number of bathrooms will tend to increase a house's sale price by $17,105.17. Again, just using that bathroom coefficient there. And now I'm going to do the super lazy thing and say ceteris paribus, right? That's Latin, that's economics for holding all else constant. I want you to try saying it a couple of different ways, try using some different language. The important things is that you're talking about the marginal change in x, the marginal effect of x on y, which is that beta hat size, talking about holding all your other variables constant, and making sure to use language that is careful. So I always am careful to say that we're going to tend to see this relationship. It is not an exact relationship, right? We know that adding another square foot of lot size doesn't always add $5.43 to a home sale price, right? There is some variation in y that's not being explained by our model. There's actually almost 40%, right? There's 47% of our variation in y is not explained by our model. So we have to be very careful with our language to say these aren't certain relationships. They aren't exact relationships. They're general trends that we can see based on our estimated coefficients and the data we have available. Okay? If you're not sure about that, let me know and we can talk about it more. We can go through and look at some of the effects. But you want to think about, like, if you go up here, right? Our model is telling us how much these estimated coefficients are going to explain this total variation in y. There's still a good amount of residuals there that our model's not explaining. And so our model is not precise or perfect. It is a good estimate, but it is not perfect, right? We can't always say everything about the real world. Okay. Last coefficient, the estimated, let's say the beta hat value for the explanatory variable stories is 7634.897, which implies that each additional, that's not right, additional, gosh, you don't realize how much you rely on spell check until you can't have it, huh? Each additional story added, each story added to a house will tend to increase its sale price by $7,634.90, holding lot size, bedrooms, bathrooms constant. There. Now I've interpreted all of my coefficients. I do want to spend some time talking about the statistical significance. Like I said, it's good practice for a lot of reasons, because you will need to do that over and over again because it's going to keep coming up on exams and stuff. I'm also going to copy my interpretations and put them in my do file. But you do want to, I don't ask you to do these things to be tedious or make you have busy work. I do it because I know that this is not the way we normally talk, right? The language we use in these interpretations and these statistical significances is not how we would normally speak. And so it's like learning a new language. You want to practice interpreting the statistical significance so that you can have a better sense of it going forward. Does that make sense? Hopefully. So let's go back and do our interpretations or our statistical significance now. And like I said, just give yourself a couple of good iterations and practice on this. So I'll start again with lot size, or actually what I'll say is looking at all 4 explanatory variables, they all have p-values below the 5% significance level, meaning we can reject the null hypothesis for each. I do want to say something about bedroom because it has a higher p-value than we're used to. So the p-value for the explanatory variable is higher than the rest, but still well below the 5% threshold. It would not be significant, right? It would not be significant at the 1% level, right? Because it wouldn't pass, the p-value of 0.02 is not lower than 0.01. So that's worth noting, I think, right? We can also say some stuff about the confidence intervals, that the standard errors are all quite low relative to the coefficients. None of the let's put it in 95% confidence. So we can be pretty confident in the statistical significance of our independent variables. That's the weird one. Cool. All right. So now we've talked about the standard errors. We've talked about the p-values. We could talk about the t-stats. We've talked about the confidence intervals. We've talked about the f-stat. So we've done a pretty good job of talking about this data set, right? So I'm going to copy this over to my do file. I decided I'm going to separate this out so it's easier to read because it can be a lot sometimes. Okay, and now I can do part B. Okay, let's get that in my log file. And so as you remember, our log file is going to show everything we've done since we opened the log. So once I start opening this log, it's going to track every command and all my results. And so that's a really useful tool for me in terms of seeing your results, and for you in terms of just tracking what you did on a given day, what worked, what didn't work, that kind of thing. But in terms of having something that you can edit over and over again, you want the do file. The do file is going to be something you can edit over and over again and be really useful and practical for you. So part B says, now we want to run the regression of y, x2, x3, and x4. We're going to skip x1. So that's going to be a regression of sale price without lot size, just bedroom, bathroom, and stories. And what do you expect our R-squared is going to do? Well, we're leaving out something that explains a lot of variation in y, so we're going to expect our R-squared to go down. What about the coefficients for the remaining explanatory variables? That's going to go up because now that lot size is removed, some of the variation in home price that was explained by lot size is going to kind of be scattered into things like bedroom, bathroom, and stories, because those things are correlated together, right? Bigger houses have more bedrooms, bigger houses have more bathrooms, bigger houses might have more stories. And so when we omit a useful explanatory variable, we are going to see the remaining coefficients capture some of that variation that would have been captured by the variable that we omit. So let's take a look at that and prove me right. So now I've got my regression of sale price on bedroom, bathroom, and stories. And, oh, I hate that little dot. That's the thing. When you copy your commands from the results, you get these little dots and carets. When you copy them from the command line, they come in nice and clean. And that's why I like to copy them from the command line, because I like it to be really clean. I don't want to edit my do file later on. Okay, so let's interpret our results. So first of all, our R-squared is lower. Our old R-squared was 0.5355. Our new R-squared is 0.35. So we went from being able to explain about 53% of variation to 35%. So we have omitted a useful variable, right? Our model is not as good as it used to be. So let's talk about that. The R of R-squared of 0.35 implies that this model explains 35% of the variation in house sale price. This is less than the variation explained by our previous model. The F stat does confirm that we can reject null hypothesis that R-squared is 0. And now we've interpreted and discussed the statistical significance of our R-squared. Now we can look at our betas. Remember, these coefficients, these beta hats, are the point estimate of the variable we're talking about. And we can just look at them and eyeball them and remember, so compare them to before. Bedroom was $2,824. Now bedroom's effect is $20,873. So that's telling us it's got a lot, or sorry, nope, that's not accurate. Bedroom was $2,824. Now it's $4,335. So it's not as big a jump, but it's still almost doubled. You can see that the p-value's gotten smaller, which means that it's more statistically significant than it was before, because it's carrying more explanatory power, right? It's capturing that variation that could have been captured by sale price. Okay. If you're having a hard time understanding that, let me know and we'll talk about it some more. I'll try to think of a good example for what that means. But the idea here is that by omitting sale price, some of the variation, or by omitting lot size, some of the variation that would have been explained by lot size is now being captured by bedrooms. So let's do some interpretations. Each additional bedroom will tend to increase house sale price by $4,335.38, holding bathrooms and stories constant. Now, bathrooms and stories are the only two other explanatory variables, so they're the only other variables we're holding constant. That's another change from our previous model. The first model, where we had 4 explanatory variables, we were holding 3 other variables constant when we were looking at those marginal effects. Now we're only holding 2 other variables constant, right? We're looking at the effect of a change in number of bedrooms, holding bathrooms and stories constant. So we're not getting as clear a picture of that marginal effect. This is, let's see, should we explain it here? Yep, okay. This is a much larger marginal effect than we saw in the previous model, and the estimated coefficient has a much lower p-value and higher t-stat. Cool. So now we've talked about the statistical significance. We've talked about the t-stat here is 3.3 in the first case, 2.33 in the first case, and now it's 3.03. We've talked about the interpretation of it. We want to copy that over into our do file. Oops. And make sure we hit enter and get it in there. We're going to see the same trend in these other variables too. So now we can look at bathrooms. It used to be about $17,000 for each additional bathroom. Now it's $20,873. So each additional bathroom in a house will tend to increase that house's sale price by $20,873.08, holding number of bedrooms and stories constant. This is a larger effect than we saw in the first model, which is to be expected. We can reject the null hypothesis for this point estimate because the p-values are low, or the p-value is low, the t-stat is high, and the confidence interval at 95% does not contain 0. Cool? Making sense? Chugging along. Copy it in. Let's go to the next variable. Now we have stories. Each say an additional story will tend to add. Sorry, I know the typing sound is kind of loud on this. I do have a cover on my laptop which muffles it a little bit, but it's still very clickety-clackety. My deepest apologies. I will maybe figure it out or not. If you have advice, happy to hear it. Always happy for your advice. Okay. An additional story will tend to add $7,539.66 to the sale price holding number of bedrooms and number of bathrooms constant. This coefficient is likely statistically significant significant because the p-value is below the 1% significance level. And the confidence interval does not contain 0. This, let's compare it to the coefficient before. So now our coefficient for stories is $7,539. Before it was $7,634. So that's not larger than it was before. And so that may make us want to wonder why we might see a different effect on stories than we saw on bedrooms and bathrooms in terms of removing lot size. And one thing to think about is the idea that having additional stories might not be so strongly positively correlated with lot size. Usually lot size is not the same as total square footage of the house. So if you think about having additional stories, that doesn't increase the footprint of the house. So that might be the effect, building up rather than building out, is interesting. So that's a little bit of a more surprising outcome, and that's something else we can talk about. We can say this marginal effect is somewhat smaller than we saw in the previous model. And that's worth looking at and kind of thinking about what that might mean. Okay, so I want to go ahead and copy that interpretation and paste it into my do file, and then now we are ready for part C. Oh, sorry. And of course, make sure I actually enter it in so it shows up in my regression results. So part C says to go ahead and do another regression, this time of sale price with X1, X3, and X4. So this time we're going to include lot size, and we're going to exclude bedrooms and just run ahead to bathroom and stories. I want to go ahead and copy that command into my do file. And then go ahead and check out my regression results. So now we see our R-squared is actually pretty high up, right? Back close to where we were before, 0.5309, much higher than the last model, right, of 0.35. Not that much lower than the first model with everything, kind of telling us that maybe bedroom is not as useful a predictor of variation in sale price than we would have thought, right? Maybe it's not as important how many bedrooms there are when we can take into account bathrooms and stories. We can see that our F-stat is really high. The p-value for that F-stat is very low. Our regression sum of squares and sum of squared residuals are behaving the way we would expect. We've got our lot size coefficient is about what we would expect, 5.5, so $5.50. Not that much bigger than before, but bigger. And this is that same effect. If we're leaving out the variable bedroom size, some of the explanatory power associated with number of bedrooms, is going to be left into lot size. So lot size is going to get bigger because bedrooms are no longer explaining some of the variation. We look at the coefficient for bathrooms and stories, and we can compare them to the previous one, where stories actually got a lot bigger than last time. Meaning maybe more of the explanatory power of bedrooms is falling into that bucket of stories than before. So if you think about these 4 explanatory variables, lot size, bedrooms, bathrooms, and stories sort of being buckets of explanatory power. If we take away that bedroom bucket, it looks like a lot of the change in explanation fell into that story bucket, if that makes sense. So the variable stories is capturing a lot of the variation that bedrooms might have before. If we compare bathroom to the first model, 18,000 relative to 17,000, it's a little bit higher, not that much higher. It's actually lower than it was when we took lot size out. And that just gives us a sense of how these variables are related to each other and to that explanatory variable of sale price. So let's do some interpretations. So I'm going to try and just kind of knock them all out really quickly here. So this model explains 53% of the variation in sale price, and we are able to reject the null hypothesis that R squared is 0. Okay, I'm gonna select and copy that and paste it in my do file, and then do my interpretations of my coefficients. A marginal increase in lot size will tend to increase house sale price by $5.50, holding bathrooms and stories constant. Each additional bathroom will tend to increase the sale price of a home by $18,166.27, holding lot size and stories constant. An additional story will tend to increase the sale price of a house by $8,399.57, ceteris paribus. Copy my interpretations over to my do file. And again, I'm not going to ask you for your do files unless you want to give them to me to have me check them out. But it's a useful tool for you. I'm going to create this do file and post it to Canvas so that you guys can take a look at it in case you have any questions. I certainly hope that you do not, you need to write your own interpretations. If I see my own text, I'm going to be super duper bummed. So please don't bum me out. Life's kind of a bummer right now anyway. Let's be cool. But it's a tool for you guys to help you get a sense of how I would do this work. Okay, last thing is statistical significance. All of the independent variables in this model are statistically significant at the 5% and the 1% level, meaning we can confidently reject the null hypothesis for each beta hat. And I'm gonna copy that, paste it over here, and then I'm gonna say something about part D. So part D, you don't have to run another regression, although it would be interesting to run a regression where we leave bedrooms or bathrooms out and a regression where we leave stories out. But we want to talk now about what is the effect of omitting a variable. And that's the point of this exercise, is to go through and look at what omitted variables will do to our regression. So let's see. Omitting a variable has the effect of reducing the explanatory power of the model, right? We took any variable out, we reduced our R squared, right? Our R squared got smaller, meaning our model explained less variation in Y. We also saw that omitting a variable tended to increase the marginal effect of the remaining variables although not always. The effect on the coefficients, on the remaining coefficients, was not standard and was likely related to how closely correlated the omitted variable was to the explanatory variable in question, which is just a fancy way of saying leaving stuff out made our model less good. It inflated the explanatory power of our remaining variables, but how much it inflated them by depended on how closely the left out, the omitted variable, was related to the remaining variables. So lot size and bedroom are pretty closely related. So it had a really big effect on the coefficient for bedroom to leave lot size out. And so again, this is where we get to this idea of you need to have a sense of the theory and the mechanisms that you're studying in order to be able to know what's going on when you look at your data. You can't just go in with some numbers and truly just purely crunch data without a lot of sense of what the theory behind them is. So that's the really cool thing about working with this data set. We understand houses, right? We've all lived in houses. We know what bedrooms are and bathrooms are and stories are. And so that allows us to have the sort of institutional knowledge, the theoretical knowledge that's needed to understand how these variables are interrelated. Okay? So that's my part D. I want to make sure to copy and paste it into my do file. Where'd my do file go? There it is. Cool. So that's half the lab. The next one is to do example 6.4, which is looking at, I'm going to be consistent in my naming conventions, part 2, example 6.4, which is going to be looking at the electric data set. I'll just get you guys started on that. So I'm going to make sure I clear out my current data, and then I can import the electric data set. Which I think that's my clean copy. Looks pretty clean. Okay. Import first row is variable names, and that's going to help me so I can see here is the cost associated with production. Here's the output in kilowatt hours. Here's the price of labor, the price of capital, and the price of fuel. So I want to make sure I get that command in my do file. And then we want to do 2 or 3 things. The first thing I want to do is summarize my data. Since we only have a handful of variables, I'll summarize everything. And then we want to do 2 regressions and interpret them. We want to do a regression of y on x, meaning y on that first x. So we want to regress cost on output, which we've done before. And you got to be careful here because now these variables have uppercase names. So a lowercase name is going to give you an error. You really have to track cases in Stata. It's obnoxious, I know, but it's the way it works. It's the way the code is written, and I am not equipped to change that. So that gives us our regression results. We can interpret them by saying this model explains 91.6% of the variation in output, output costs. In production costs. stat is large enough that we can confidently reject the null hypothesis, and copy that over. All right, just run them down. And then we just have, in this model, this first iteration, we just have one coefficient to interpret, one p-value, one confidence interval. You want to remember, and you can always go back to the lab here, and I put your units into the lab so you can remember that. So we're looking at the marginal change of output in 1,000 kilowatt hours per year is going to have a beta hat size effect on the cost of production in millions of dollars per year. Okay, so we can interpret that coefficient as saying an additional 1,000 kilowatt hours of output is going to tend to have the effect of increasing costs by 0.00478 or 0.005 times, what is our units again? I'm sorry, $1 million. So by 0.005 times 1 million is 5,000. So a increase in output of 1,000 kilowatt hours will tend to increase production costs by, I'm going to be more precise, I'm going to say 4,000. The book rounds it up to 0.005 and then says $5,000, but I think it's nice to be a bit more precise and say $4,780. We aren't holding anything else constant because there are no other explanatory variables, meaning we have no control variables, but this is statistically significant. So this this explanatory variable has a small p-value and a small standard error relative to the coefficient, the estimated coefficient. So we can reject the null hypothesis. And you can see here the confidence interval is small and close to 0, but it does not contain 0, and that's what's important. So I can copy this over. And then the last step you're going to want to do, the last two things you're going to want to do is you're going to want to do a multiple regression where we're going to use all of our explanatory variables. So we're going to use cost, output, the price of labor, the price of capital, and the price of fuel, and then interpret those coefficients. And so we're going to be talking about, a marginal change in the price of capital and the effect it has on millions of dollars per year of cost. You want to look at your statistical significance. You can see here, price of capital is borderline, doesn't contain 0, is below 0.05. We can see our R-squared did go up, not by much, but we didn't have a lot of place to go, right? So now our model explains 93% of the variation in cost. And so we did see an increase to a certain extent, but not much, but that's because we were explaining a lot already. The last thing you're going to want to do with this assignment after you go through and discuss these results in the same way we have before is to generate a correlation matrix. And when we talked about this in the Zoom, someone asked if we wouldn't do that automatically, like first thing when you get your data. And yeah, generally, I think it's useful to, anytime you approach a new data set, summarize the data, make sure that the mean and the standard deviation and the minimum and maximum look like what you expect them to look like. Also, when you're looking at your summaries of data, you want to make sure that the number of observations is the same, that you don't have missing data. You'll have to clean that if you do. And then you do want to do a correlation matrix. And again, correlation matrices are easy to do in Stata, much more complicated because you have to calculate each correlation coefficient in Excel. But we'll cross that bridge when we get to it. And so that gives you a good sense of it. And so if we look at this correlation matrix, we can look first at how all of our variables are correlated with cost. And we can see, of course, output is highly correlated with cost, which explains why that simple regression does such a good job of explaining the variation in cost. Price of labor is not very highly correlated, nor is price of capital. Price of fuel a little bit. And then if we looked over here and we wanted to see which one we might accuse of being possibly having a multicollinearity problem, you want to look at explanatory variables that have the higher correlation coefficients. And like I said in Zoom, there's not a hard and fast rule on this. You can compare them to each other more than anything, but that's what you want to kind of look at, is the relative correlation coefficients and see sort of what stands out there. And so I'm going to pop that command into my do file. And I think I've gone over a lot of this stuff for you guys. I think I've given you a lot to build off of. Please let me know what questions you have. A little bit later on, I will post the do file. I'll put the video up first and give you guys a couple of days to ruminate over that and kind of process that. And then I'll post the do file for you guys and my log file. In the meantime, let me know what questions you have. Make sure you check Canvas for announcements and wash your hands, stay safe, stay inside, and keep in touch. All right. Thanks so much, guys. One last thing I forgot. What you're going to want to make sure you do if you are going to be submitting my log file to me for this lab is you want to make sure you go up and go ahead and close your logs. So you can do that either with the little log menu there where it'll give you the option to close it, or you can go here to log and then close. But you want to make sure you don't close your log until you're completely done, because once you close it, you cannot open it again. What you could do is either select this text and paste it into a Word document, or open up your multiple logs and paste them into a Word document together, but log files are really finicky. So once you close it, you can't open it again. So I will close my log because I'm done. But make sure that you do close your log when you are done, and don't close your log before you're done. And then I'm going to pop that last command into my Stata do file so that I know that that's when I'm done. Okay, that's it. Now we're done.